All right. Okay, so we are starting chapter 16. Now, on the board, if you're watching the video, you can't see, but click on chapter 16. We're going to skip 16.1 because all they're doing is computing the domain of functions. Except now we're talking about functions of several variables now, not just one variable. So we're going to go basically 3 and higher dimensions now. So we're going to start with 16.2, which is the quadric surfaces. Like in 2 dimensions, we had the conic sections. But in 3 dimensions, we call them quadric surfaces. Okay, so tonight's homework is 16.2. I put it on the assignment sheet, 16.2, and we're only going to do the starred problems. You know why? Because the answers are given in the back of the book.
So just 1 through 11?
1 through 11 odd, and then 19, 21, 23, 26, 28, and 30.
Oh, so much.
Okay, don't do it then.
Okay.
Get a 4 on the next test.
That's
Okay, now where do you find the answers to this? Where do you find the answers? Oh, right here, chapter 20, answer to starred problems.
Wait, I don't have chapter 15.
We're in chapter 16.
Why is that in chapter
What?
15? Never mind.
What? Wait. What's going on? Okay, and then the next night's homework, I just want to make sure you guys know everything. Next night's homework, we're going to skip 16.3 because I'm going to actually talk about it in 16.2. Then we're going to learn how to take partial derivatives. See, partial derivatives. It's easy. We're going to skip 16.5. And then we're going to go on to 16.6, mixed partials.
So we're skipping 16.1 and 16.5.
And 0.3.
Just one more.
Okay, so basically today we're going to learn about the quadric surfaces. We're going to learn how to sketch 3-dimensional surfaces as well. Okay, I'm just going to leave that up there. I don't think we really need it. Okay, so let's start talking about sketching graphs. Now we already talked about sketching planes, right? But let's do it again for funsies. Let's say you have a plane. 2x plus 3y plus 4z equals 12. How do we know that's a plane? Because it's a first degree equation, right? All the variables are to the first power. That's going to be a plane. Now, how do we sketch it? Remember, we sketch it in the first octant. Plot the x-intercepts. Well, just the intercept. What's the x-intercept? 6. So here's the point. 6, 0, 0. What is the y-intercept? 4. 0, 4, 0. What is the z-intercept? Rhymes with mean. 3. Now, when you graph 3-dimensional surfaces, intercepts are not enough. So we also have to graph. We talked about this in PCH. I don't know if you guys did. Ha and Park.
Probably not.
Not just intercepts. We talk about the traces. Okay, there are 3 traces. You got the xy trace. You got it? The xz trace. And then the yz trace. Now, what the heck is the xy trace? The xy trace is where the graph intersects the xy plane right here. Now, in the xy plane, what can you say about the z coordinate? In the xy plane, it's 0. So to compute the xy trace, you simply substitute 0 for z. Like right there, and you get 2x plus 3y equals 12. Hey, that's a line. So whatever this graph is, well, we know it's a plane. Whatever this graph is, it intersects the xy plane at that line, which is this. Of course it extends, but I'm just drawing it in the first octant only. And then and likewise, what do you think the xz trace is?
2x.
Where the graph intersects the xz plane on this wall right here. Okay, so how do you think we're going to find that? Because what's the equation of the xy plane? I mean the xz plane.
It's 2x
No.
plus
What's the equation of the xz plane? No, it's y equals 0. Because all the y coordinates are 0. So all you have to do is set y equal to 0 and you get 2x plus 4z equal 12. Hey, that's one line. Yeah, that's this line right there in the xz plane. And then finally, as you can probably guess, the yz trace is where the graph intersects the yz plane, which is this wall right here. And how do you think I'm going to find that? Set x equal to 0, and then you get 3y plus 4z equal 12. Hey, that's one line. Yeah, that's this line right there. And then use your shading techniques, your artistic, I'm not very artistic, shade it in. Woohoo! So this is the plane cutting into the first octet like that. Yeah, but see, that's easy because it's a plane. It's like the easiest graph, one of the easiest graphs you can draw in 3 dimensions. Let's kick it up a notch. Okay, let's x squared plus y squared. No, x squared over 9 plus y. No!
Oh my
16
god.
plus y squared over 9
Huh?
plus z squared over 4 is equal to 1.
Oh,
What do you think this graph is?
that then on the left.
Yeah, an ellipsoid. Okay, but let's say we don't know what this graph looks like, because you're gonna have to start drawing 3-dimensional graphs, people. See, you had a taste of it in PCH, but like I said, you guys forgot it. Okay, let's do the intercepts first. What are the x-intercepts? Park, x-intercepts.
4.
No,
The x intercepts.
look, I even said it, the x-intercepts.
Oh, the 4 negative.
Plus or minus 4, right? Because
Yeah.
to find the x-intercept, you set y and z equal to 0. If x squared is 16, x is plus or minus 4. So, here, 4. I'm just going to put 4 there. And negative 4. But again, if I ask you to graph outside of the first octet, then you're going to make dotted lines going back, and it's tough. So if I'm going to make you graph, probably it'll be only in the first octet, unless it's not. Okay, what is the y-intercept? Plus or minus 3. So you're going to have 1 over here, but then you're going to have 1 on the opposite side there, but we're not going to draw that. And what is the z-intercept? Y? 1
Plus or minus.
1.
plus or minus 2. So here's 2 and they got negative 2 there. Now, do I connect it with straight lines?
No!
No, well, if it was a plane you do, but now we got to look at the traces. I'm going to just use these. Let's erase. How do you find the xy trace? How do you find where the graph intersects the xy plane?
Plug in
You
0.
said z equal to 0, and then you get x squared over 16 plus y squared over 9 equal 1. Hey, you want ellipse! But you're drawing it in the xy plane. So here, in the xy plane, how do you graph this ellipse? You go 4 to the right, 4 to the left, 3 up and 3 down. It's like that, right? Okay, but now look. Here's the xy plane over here on the floor. We're only looking at just that part of the ellipse there. So that's this right here. See how it's not a straight line? And it's perspective too, right? Okay, what is the xz trace? Where the graph intersects the xz plane, right here. So you set y equal to 0. Hey, you want ellipse? X squared over 16 plus z squared over 4 equals 1. So in the xy plane, this is where the graph intersects it. So here's the xz plane right here. 4 and 2. It's an ellipse. And then as you can probably guess, in the the yz plane, trace, what do you have to do? You set x equal to 0, and you get y squared over 9 plus z squared over 4 equal 1. Hey, that's one ellipse. But that's in the yz plane right here. And then you use your shading techniques. I need a full piece of chart. Oh, this is a full piece of chart. Shade in. So what fraction of the ellipsoid is that?
1/2.
4 and 8.
1/8. That's only the first octet. That's 1/8. And if you want to see it, here, look at the picture in the book, right here. Ellipsoid. But that's too, like I said, it's too difficult to graph it in all octants. That's why first octant good enough. Park, question? Okay, are we ready to kick it up a notch? We have to. This is called an ellipse. So this is 1/8 of the ellipsoid. Okay, before we move on, an ellipsoid is a. Joe, am I boring you?
Oh no, I have to stretch.
An ellipsoid is an example of what we call a quadric surface. Now, let's go back to pre-calculus. In 2 dimensions, any graph that has this form, ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0, will be a conic section. And you guys remember how we learned to identify the conic section? B squared minus 4ac. If it's greater than 0,
Parabola.
hyperbola. If it's less than 0, ellipse. Equal to 0,
Parabola.
parabola. If it's a non-degenerate conic. Remember that word from PCH? Because sometimes you have a graph that, here, since we're high up, we can understand this. Look at this. Shh, I'm thinking. Let me ask you this. What is the graph of this in 2 dimensions? If I were to graph that on the xy plane, what would it be?
A line.
A line. What if I square it?
It's a parabola.
No, it's the same line.
What?
It is?
Oh gosh. Okay, what if you have this, x minus 2 equals 0? Isn't that just the line x equal 2, right here? Vertical line.
Yeah.
What happens if I square this? Isn't it still x equals 2?
Oh yeah.
This is not y equals now, this is equals 0. It's not y equals. See, if it was y equals, then that would be a parabola, but this is equals 0. Okay, let me ask you this. What value of x will make that 0?
2.
2, so x equals 2. What's the solution to this equation?
Oh, it's.
X equals 2. It's still a vertical line.
Okay.
Okay.
Do we get, what if I cube it?
It's the same.
Yeah, it's still a vertical line. Okay, so same thing here. If that's a line, that's a line.
Okay.
Okay, it's the same thing. Okay, now let's actually multiply this up. Okay, we should know how to go a plus b plus c quantity squared, right? This is a math team thingy. How we learned this even when you were 9th grade. X squared plus y squared plus 1. So you square each of them. You know what? I'll just write it up here. A plus b plus c squared is equal to a squared plus b squared plus c squared plus 2ab plus 2ac plus 2bc. Does that even look familiar? Came up in PCH, I know. Anyway, so that plus 2 times this plus 2 times that plus 2 times that equals 0. Hey, that looks like a conic section. In fact, let's write out the first 3 terms. X squared plus 2xy plus y squared and the other stuff. So according to what we learned in PCH, b squared, see this is a, b, and c, b squared minus 4ac comes out to 0. It's supposed to be a parabola, but it's not, it's just a line. We call this a degenerate conic. In other words, it looks like it should be a parabola, but it's not. That's why it's degenerate. Anyway, when we studied this in PCH, we only did the non-degenerate conic. So if b squared minus 4ac comes out to 0, when we studied in PCH, it was an ellipse. But a parabola. I just want you to know, just because it looks like it might be a parabola, it could be something else. It could be a line like this. So you gotta watch out for that. Anyway, in 2 dimensions, the general 2nd degree equation will be a conic section, right? And what are the conic sections? What do we have?
Parabola.
Okay, remember what the conic sections are? If you put 2 cones nose to nose like that, And then, of course, it extends forever, right?
Hyper.
And then you take a plane and you intersect it. Anytime you intersect a plane with these two cones, you get a conic section. So what can you get? Ellipse,
Hyperbola.
hyperbola,
Parabola.
parabola,
That's it.
circle, like if you intersect it like that.
Yeah, you're.
What about a single point? Like, right there. Yeah, a line. Like what if you intersect it right along that edge there? A line would also be a conic section, right there. In fact, there you go. That's- Anything else? How about two intersecting lines, two lines? Like, what if you intersect it right down the middle like that? A plane, right down the middle. Aren't you gonna get the two intersecting lines like that?
Mm.
Oh, yeah.
Yeah. And remember, the conic section, these are hollow cones now. It's not like filled in, yeah. Okay, so that's your review of 2 dimensions. Now, in 3 dimensions, do we have something similar? Yes. So in 3 dimensions, anytime you have an equation of this form, which is second degree, that means the highest power is 2. Ax squared, how should I write this? Plus by squared plus cz squared plus dxy plus exz plus fyz plus gx plus hy plus iz plus j equals 0. Anytime you have an equation of this form in 3 dimensions, you're going to get?
Conic.
No, this is
Oh,
conic section.
quadric surface.
Very good, conic section. We call it a quadric surface. Okay, so what kind of quadric surfaces can you see? Well, that's what the book has, so you might want to look at the book and look at the pictures and look at the equations. So, on this next test, what you're going to do is I'm going to give you an equation, you have to identify the quadric surface.
That's it.
Yeah, so the easiest thing to do, I think, is to look at the intercepts and the traces. Unless you just want to memorize.
Which is easier.
I don't, there's not that many quadric surfaces. Okay, let's look at, okay, we did an ellipsoid. What about a hyperboloid? Now, the trouble with this is, there's 2 different kinds of hyperboloids. Because think about it. What if you have a hyperbola like this? What if I ask you to revolve it about this line? You have a hyperbola. What happens when you revolve it about this line?
You have 2.
Yeah, you get these like 2 cups. We call that a hyperboloid of 2 sheets because you need 2 sheets of paper or whatever to make it. But what if you have a hyperbola like this and you revolve it about this line over here?
Oh, looks like a.
You're gonna get like something that looks like that, right? We call that a hyperboloid of 1 sheet because you can make it out of 1 sheet of paper. So each of these things has a particular equation. Now, since I have it on the board right there, look at number 2. Hyperboloid of 1 sheet. Okay, let me give you an example. X squared over 4 plus y squared over 9 minus z squared over 1 is equal to 1. Now notice, see, if they were all plus signs, you know that's an ellipsoid, right? But now, if one or more of them is a minus sign, what do? Well, if you got 1 or 2 negative signs, that's going to be some kind of hyperboloid. So how do you figure out which one? Let's look at the intercepts and the traces then. Okay, what are the x-intercepts? Plus or minus 2. So we're going to have 1 here and then 1 on the opposite side. We're not going to draw that. What are the y-intercepts? Ooh, plus or minus 3. 1 over here and 1 on the opposite side, but we're not drawing that. What are the z-intercepts?
1.
No more! No more,
No
because
more.
look, if you set x and y equal to 0, you get z squared equal negative 1. That's imaginary, so no more, because we're only graphing real numbers here, yeah?
Oh yeah.
So this graph does not touch the z-axis. Now let's look at the traces. Why did I erase that thing? XY trace. How do you find the XY trace again? Where it touches the XY plane? You said z equal to 0. and you get x squared over 4 plus y squared over 9 equal 1. Hey, that's what ellipse. So the trace in the xy plane is like that. That's where it hits the xy plane. Now let's do the xz trace. How do you find the xz trace? You set y equal to 0, and then you get x squared over 4 minus z squared over 1 equals 0. Hey, that's one hyperbola. But you gotta graph it in the xz plane. Now can you imagine that? Like, you could just do it like this. Look, if this is x and this is z, I gotta go 2 to the right, 2 to the left, 1 up and 1 down. I gotta make the rectangular box, draw in the asymptotes, and since the x comes first, it's gonna be left and right like that, yeah? But here's the xz plane right here. How do you draw that right there? What's gonna happen? Look, here's the positive x-axis, here's the positive z-axis. So, like this then, oh gosh, I'm bad at drawing. Like that? It's kind of weird. Yeah, that's it.
Wait, I think you said there wasn't.
It's not on the, it's like a flat.
That's the, see, this is the positive x, that's the positive z. So, positive x, positive z, so that means you gotta go on the other side of the board and look this way to see this. Look, this is the positive x, this is the positive z, right?
Yeah.
But this is the positive x and positive z. So you gotta kind of do this.
Wait, why
To be in
is
that
there an
orientation there.
xz trace if the graph doesn't touch the z-axis?
It doesn't touch the
It's
z-axis.
just
Look,
like
the graph is going that way.
It's just flat.
XZ trace is where it intersects the XZ plane.
XZ plane.
The plane, this wall right here. This wall, the XZ plane. What's going on, Cho? And then finally, the YZ trace. Where does this graph intersect the YZ plane? Well, we're gonna set x equal to 0, and then you get y squared over 9 minus z squared over 1 equals 1. Hey, that's one hyperbola! So here's the YZ plane. So how would you graph this? Is it gonna open left and right? So it's gonna look like that, yeah? So which of these hyperboloids do you think it is?
One sheet.
Yeah.
How do you know? Because it says in the book right there, hyperboloid.
It's connected.
Yeah, exactly, it's connected, that's right. Because, yeah. So you have to do whatever it takes to figure out what the graph is. I don't know, some people the previous years just memorize them. Some people do that, whatever you have to do to figure it out.
Do you have to drive?
I'm gonna make you draw some things, but hyperboloids are kind of hard to draw. Okay, now let's do a paraboloid now. Now sometimes just graphing intercepts and traces, that's not enough. So we gotta learn another technique. This is the one we're skipping. Let's look at a paraboloid. X squared plus y squared is equal to, give me a number.
But that was a hyperboloid. The last one.
3.
That's a hyperboloid of one sheet.
So,
Okay, we're doing a paraboloid now. How about 4? No, let's just go z then. How about just z?
so there's 2 negatives in the 2 sheet, or
Or you want me to memorize for you?
no?
Yeah, I mean, if you want to memorize, there's certain ways of doing it. Or
So
if there's
like
one
a-
minus sign, it's one sheet. If it's 2 minus signs, it's 2 sheets.
Is that true?
Well, look at the thing. Okay, let's scroll down. Darn it. Okay, look. Where's the 2 sheets? Oh, see, you got 2 minus signs.
Huh?
Okay.
If you make one side of the equation 1, see, but they made it negative 1.
Oh.
See, so if this side is a 1, wouldn't you have 2 negative signs?
Negative x and negative y.
Yeah. See? Oh, that's right there. It's a good way of memorizing it, right?
What, they're all negative?
Okay, so if this side is a 1, if you got 1 minus sign, it's a hyperboloid of 1 sheet. If you get 2 minus signs, that's gonna hyperboloid of 2 sheets. I just gave away the secret.
Well,
Do you have
3.
3 sheet hyperboloid?
No, there's no 3 sheets.
Is this something else in this group?
Okay, oh, is that what it is? What if they were all minus then?
It also exists.
Yeah, there's no graph. Because look, if you multiply both sides by -1, like that, how can you add 3 squared quantities and get a positive number? I mean, get a negative number. You cannot, right?
Imaginary.
No, yeah, but we're only graphing real number. Okay, let's go to the paraboloid now. How do I know this is a paraboloid?
On the trace.
It's got two.
Okay, well let's try certain things. X-intercept,
0.
0.
Wait.
Yeah.
Set y and z equal to 0. Y-intercept,
0.
0. Z-intercept, 0. That's all we got. Okay, now what about the traces? What is the x, y trace? Set x, z equal to 0. So here, let's do it again. X, y trace is, what happens when you set the z equal to 0? You get x squared plus y squared equals 0. What the heck is that graph?
An origin.
Yeah, it's a single point at the origin. Right? Because again, the only way you can take 2 squared quantities to get 0 is 0 plus 0, right? Okay, x, z trace. Set y equal to 0. You get x squared equals z. Hey, this one parabola. Right? That's kind of like y equal x squared, but it's z equal x. See, it's like this, look. If it's xy, what is the graph? Isn't that y equal x squared? So if this is the z-axis, wouldn't it be z equals x squared? Same kind of thing. So what would that look like?
No.
I'll try to draw it like that. Okay, and then finally, what about the yz trace? Set x equal to 0, and then you get y squared equals z. This one parabola in the yz plane, it's kind of, that would be the trace like that. So you can kind of imagine the paraboloid, kind of like that. Now there's other ways to think of what the thing is. This thing is called level curves. Level curves. So this will also help you either visualize, or if you're sketching 3-dimensional surfaces. Like when z is equal to 0, what does this graph become? What does this equation become? X squared plus y squared equals 0, which is a single point right there, yeah? But what happens when z is equal to 1?
Circle.
You get x squared plus y squared equal 1. Hey, that's a circle of radius 1. Yes, but that's only when z is 1. Now, where is z1? 1 unit above the xy plane. So 1 unit above the xy plane, you're going to get a circle of radius 1. You guys seeing that? Okay, what about when z is equal to 4?
2 radius.
You get x squared plus y squared is equal to 4. Hey, that's what circle of radius 2. So, when you're in the plane z equal 4 up here, you're going to get a circle of radius 2. And so forth. So every time you take a level curve, probably z equals 9 would be the next good one, yeah? You're going to get x squared plus y squared equal 9, which is a circle of radius 3. So 9 units above the xy plane, if you keep on going, you're going to get a circle of radius 3. So every time you're cutting it, you get circles. Boom, paraboloid. Call that a paraboloid. Now, I'm not going to spend the whole time going over everything. You guys need to discover things for yourself, that's why. But one of the neat graphs is called the hyperbolic paraboloid. I have a picture of it right here. Wait, I'm gonna zoom the camera in on the hyperbolic paraboloid.
I don't want to be in the video.
The hyperbolic paraboloid. Let's see if I can
Why don't you take the picture to the...
take the picture to the camera. Too late. I'll just zoom in.
It's just a picture.
Hyperbolic paraboloid. Right there, baby.
It's
How come it's not focusing?
It's actually different.
Why is it not focusing? What kind of junk camcorder is this?
It's like a sign.
Oh, I didn't even realize that. I thought it was like a water level thing.
Yeah, the hyperbolic paraboloid, look, has a very interesting point. If you're in my PCH class, I told you this. You see this point right here? Like if you talk about it in this plane right here, isn't that point a minimum?
Yes.
But if you take it over here, if you take a cross section here, it's like that point is also a maximum.
Oh.
So we have a point that's both a maximum and a minimum, which is kind of crazy, yeah? You know what we call it? A mini-max. It's called a mini-max. Or some books call it a saddle point because it's like, you know, a saddle, you put the saddle on the horse.
Sure.
You guys know what a horse is?
Yeah.
What about a saddle so you can sit on it?
Yeah,
That's what it's, saddle point or mini-max.
not maximum.
No, it's not called a maxi-min. It's called a mini-max. Look, I'm just relaying the information to you guys. All right, so tonight's homework, you guys need to get used to these quadric surfaces.
It's only,
And we didn't go through all of them, so you guys need to like learn them. Look at the traces, look at the intercepts, look at the level curves if you have to. Or if you want to just purely memorize them all, you can do that too.
so only the hyperbolic paraboloid has a mini max.
Yes.
That thing.
Oh no, I'm sure there are other